Okay. Hello, everyone, and thank you for joining us today for our Quantum Speaker webinar series hosted by ATARC Global Quantum Working Group. I'm Lily Chen, the group's government co-chair. We are very excited to welcome Dr. Swamit Tanu to speak with us today. Swamit is an assistant professor in the computer science department at the University of Wisconsin at Madison, where he leads the Quest research group. In this talk, he will focus on two critical issues that shape the path toward fault-tolerant quantum computing. If you have questions, please use the Q&A feature. We will save our Q&A for the end. Now, let's welcome Dr. Swamit Tanu to give us the talk.
Thank you. Thanks, Lily. Thanks for the kind introduction and thanks for inviting me. So today I'll talk about what is the role of system architecture when we are building fault-tolerant quantum computers. And let me start with the basic question, why do we need a quantum computer? Because we have conventional computers or classical computers that are growing in abilities to do computation. So this is the data from Oak Ridge National Lab, and even when Moore's law was slowing down, we could see a significant improvement in capability of conventional computers. So this data is for supercomputers at Oak Ridge over the years, right? But even with this growing compute capability, there are certain problems that we cannot solve using conventional computers. For example, the problem like factoring large numbers. If you want to factor, let's say, 2048-bit number, a very large supercomputer, let's say that's of the size of Germany, Netherlands, and part of Belgium's combined together, and that supercomputer, let's say, takes all the energy of Earth, even then it will take more than 100 years to factor this number, right? So there are certain computational problems that are just beyond the capabilities of conventional computing. And luckily for factorization, the quantum computers can enable a very efficient algorithm. And with this algorithm, you can factor this number in few hours, right? So these are the estimates from Google, and they are constantly changing. In fact, in last couple of weeks, they have improved the efficiency of these factoring systems even more, right? So this is like a continuously evolving field, and it's not just problems, algebraic problems like factoring numbers or breaking cryptography. There are really important problems in chemistry. There are really important problems in logistics, energy that can benefit from quantum computing. So the hope is that a quantum computer can solve some of these exponentially scaling problems in polynomial or even in super polynomial times, so that we can solve some of these really hard problems that we cannot solve using existing computers, right? But if we think about quantum computers, quantum computer is an accelerator. It's not really solving all types of problems. There are very specific kind of problems that quantum computers can accelerate, such as factoring numbers, simulating quantum systems, searching through a large unstructured database, and people will hopefully figure out even more applications that we can accelerate using quantum computers. So just to give an analogy, graphical processing units or GPUs, which are very important now because of machine learning workloads and machine learning applications, it was essentially built to do graphics processing. And over the years, GPUs evolved to do more than just graphics, and now they are just everywhere, right? So similarly, quantum computers are also domain specific accelerators. And we can think about quantum computers having two parts. One is the quantum bits, which are built in physics departments, and now engineers are taking over and trying to scale these quantum bits. But there is the other part, that is control electronics, and that also requires a significant effort when we are scaling and when we are building fault tolerant quantum computers. So my background is computer architecture, and my focus is understanding how we can interface this control electronics with quantum bits, and how can we interface quantum computers with conventional computers and scalable manner, right? So quantum computers, although they are accelerator, they're fundamentally different compared to classical accelerators such as GPUs, right? So GPUs or any other accelerators that leverages parallelism, that improves efficiency of computation by reducing constant factors, right? Whereas quantum computers just changes the complexity of the problem because we are using quantum information to do computation. So this is an example of search. Let's say you are doing unstructured search using GPUs. You can get a lot of benefit by using parallel threads. But what quantum computers offer is a completely different and reduced complexity, right? So rather than we requiring n over m steps, we require square root n steps, and that just changes that just changes the landscape of this problem. But at the same time, quantum computers also require a lot of bookkeeping. They introduce huge constant factors. And in this talk, I will explain where are these constant factors coming from. And we at Wisconsin, we are thinking about how we can reduce these constant factors, how we can make quantum computers more efficient. And just to give you a parallel between classical microprocessors and what we do, we take similar approach that computer architects have taken for over last 40 years or so. So this is the data of how processing power has evolved, and there were two contributing factors. One is transistors becoming smaller and smaller, which is a process impact. We figured out better materials, we figured out better manufacturing techniques, and we increase the number of transistors on a chip, right? But at the same time, architects sort of figured out how to use these transistors in creative ways, right? And the performance gains that we see are over more than 2000x, meaning the computer that you could build in 1980s or 19 late 1980s and computer that you built in, let's say, in today, there is a 2000x or even more improvement in performance, right? And this came from both the technology and also system architecture, right? So for quantum computers, we think it's also important to focus on system architecture aspects, not just the technology, because that is really important. But let's first understand what is it that gives this benefit to quantum computers, right? So if you think about quantum computers, there are quantum bits or qubits. They encode information in an entirely different manner compared to conventional computer, which uses classical bit, which can be only in one or zero state. Quantum bits have a richer information representation. So we can encode a vector rather than just a bit using one device. And when we use a large number of these qubits, we can represent a exponentially growing state space that we cannot do with classical bits, right? So on a quantum computer, operations that we perform are on these devices, and effectively what these operations do is they rotate this vector on this Hilbert in this Hilbert space or on this sphere, right? So any point on this sphere can be a quantum state, whereas a classical bit or conventional bit can be only in two states, one or zero. Right? But at the same time, we have this analog-like information. You have a continuous space that can be used as a quantum state. And when you are, let's say, performing operation, it's very easy to get errors in computation, right? Imagine you're rotating your state by a certain angle. It's very easy to have under rotation and over rotation. There is no quantization. So the computation tends to be very noisy and error prone. And to solve this problem, we use quantum error correction, where we use many noisy physical qubits. We run a error correction protocol on these noisy physical qubits to create one logical qubit that can tolerate errors, right? And that's essentially the path forward that many companies and academic groups are taking, where companies like Google, IBM, Microsoft, they are trying to build large scale machines where we can run error correction. And today we have maybe a couple of logical qubits already demonstrated, showing that by using error correction we can suppress errors, and there is a viable path forward to build fault tolerant quantum computers, right? And The idea is today, the machines that we can build, they have failure rates 1 in 1,000. And as we increase the number of physical qubits, maybe noisy physical qubits, by running error correction, we can reach target failure rates of 1 in 1,000,000. And that's really required because the algorithms that we want to run, let's say for factoring numbers or simulating quantum systems, they have millions of operations. So we really need ability to do fault tolerant operations, or we need the ability to suppress errors. And that's essentially what error correction enables. But in order to build this fault tolerant quantum computer, we also require a lot of classical resources. So today, to control 54 qubits, Google uses 54 FPGAs. FPGAs are field programming gate arrays. These are large chips that you connect to uh, qubits, and they are not very they are very expensive. So if we linearly scale FPGAs, it's going to be an unsustainable problem in terms of both economics and complexity. So we really need creative solutions. We need systems architecture focus so that we reduce this classical overhead while we are building large scale quantum computers. And that's essentially what we focus on. And quantum computing is really a full stack problem because we encode information in an entirely different manner, and we have several constraints that are very different from classical computing. We need to support those primitives at every level of compute stack. So this is a typical compute stack that computer scientists use for solving problems. So let's say you have a problem. First, you figure out an algorithm, then you write this algorithm using your favorite programming language. You compile it down to a binary, and then this binary runs on a computer, right? So similarly, for quantum computer, we have to create these abstraction layers. This is just a replica of classical abstraction layers. For quantum, this abstraction layers might look very different because there is quantum error correction involved, and this is kind of an open area of research that people are working on. So one of the things we worked on as a group was improving readout for quantum bits. So the basic or fundamental tasks that error correction does is it computes some redundant parity information, and you need to do a qubit readout. So qubit readout shows up everywhere, maybe whether you are running error correction, whether you are doing some computation without error correction, or even if you are just testing your device, qubit readout is a really important task, right? And the way it is performed is by using these FPGAs or control electronics, where you convert the analog information and you work on this digitized information, run some machine learning algorithms or run some classifiers to classify this qubit state bit in 0 or 1, right? When you do a readout, quantum state collapses and you get 0 or 1 information, but it's a very sensitive device. So the readout that you do needs to be very accurate and aware of the intricacies of the device level things, right? So we've been working on superconducting qubits and neutral atom qubits, and our goal is to improve the readout fidelity or readout or suppress readout errors without increasing complexity. Because when we build a fault tolerant quantum computer, we require millions of qubits, and maybe on the half of the qubits we need to run readout in parallel, right? So we really need a lightweight readout protocols, and we want these readout protocols to be very accurate. So a lot of our effort has goes into building classifiers that we can run directly on FPGAs and that are very accurate. Okay, so just to give you a bit of a context, right? So the way the computing model works on a quantum computer is you have a quantum program. Typically, it's a quantum circuit. You compile it down to schedule of operations that you can perform on a physical hardware, and then you run this for multiple trials. right? One reason you may want to run it for larger number of trials is because maybe there are errors, and also the quantum readout is stochastic, or it's probabilistic, so you have to run your program for multiple trials. So this is one source of constant factor, right? That we have to satisfy when we are running computation on a quantum computer. Um, and when you're running this computation, there are other constraints. For example, this is a die shot of IBM's quantum chip, and we can simplify this to this schematic where we have this graph shows 6 qubits, Q1 to Q6, and you're mapping some variables on these devices, and that's how you program, and that's how you do computation on a quantum computer, right? So one of the basic computation primitive is a 2 qubit gate, which can entangle two variables. So here, let's say variable A and variable B, we want to entangle, but you can only entangle two sort of qubit devices if there is a physical connection. In this case, there is no physical connection, but what we can do is we can move these variables around. So let's call this a data movement operation. We can do that with swaps, and after moving this data, we can perform a C naught or entanglement between A and B, right? So compiler is in charge of inserting these extra operations. Programmer just writes a program or algorithm that they want to execute, but then compiler figures out what operations are physically possible and what operations are not possible, and it inserts these extra data movement operations, right? But on the existing quantum computers where we are dealing with a lot of noisy operations, the swap operations themselves can fail. And in addition to that, there is a lot of variability on quantum computers. Not all qubits are created equal. So you have to address this issue by doing a noise aware compilation, and that's something that we have been working on for some time, right? So the idea here is understand how your hardware behaves and then use that data when you're mapping your quantum program or quantum circuit on the hardware. And it's not just the uh, mapping problem, but it's also how you navigate this n executions that you do. For example, let's say you have a quantum program, there are certain qubits on your quantum computer that are uh, prone to noise, right? So you figure out a best mapping, and now you have to run this program for n trials. Now, if you use the same mapping for all your trials, you can get time correlated errors, and that can skew the output distribution. But instead, if you use different maps, you can reduce these correlations. So how you map, how you execute, all those things are really important when you are working with quantum computers. So noise is the biggest issue, and we build software that reduces this noise in creative ways. Once you deploy error correction, this problem becomes even more complicated, because with error correction, you can only do certain operations on a fault tolerant quantum computer. So this is how a quantum compilation workflow looks like, where you have an algorithmic circuit that user specifies, and there are only subset of operations that you can do, such as, like, let's say, Clifford plus T. This is like the most sort of popular instruction set architecture on a fault tolerant quantum computer. And then you have to build or synthesize all the other operations using these subset of operations, and that's a really hard problem. So we've been looking at this problem for some time, and we have developed several compilers at Wisconsin, which not only reduce the number of operation, but also specifically focuses on really expensive operations such as T-gate. So and all these compilers are open source, so community can really use these compilers to optimize their quantum programs when they are running it, may it be on IBM machines or QERA machines or other vendors, right? So we work with a variety of technologies, and our goal is to minimize noise by reducing operations, and that's something that our compilers do really well. Uh, at the same time, we also think about how future quantum error corrected computers would be built, and how would we run computation on those quantum computers, right? So as I mentioned, we use multiple noisy physical qubits to create one logical qubit. Uh, but while we are running this error correction, it's a complex protocol. We have to do a lot of parallel tasks, and these parallel tasks can make execution model very complex, right? So you are continuously running error correction to detect errors, and then the detection of error, which is called decoding, it's also a non-trivial classical requires non-trivial amount of classical computation, right? And when you are working with millions of qubits, there is a lot of things happening on this quantum computer. So you need you need methodical ways of reasoning with these parallel tasks. And recently we have introduced this idea of synchronizing these quantum tasks, so that we can leverage the parallelism that's available on these fault-tolerant quantum computers. While we are thinking about how to build future fault-tolerant quantum computers, we also look at existing problems. One of the biggest problem that we have today is we don't have a lot of quantum computers available for users. Although these are noisy quantum computers, so this picture shows the IBM's 127 qubit machine that you can access. Uh, but there are not a lot of quantum vendors. There are not a lot of machines offered by IBM. So the wait time on these machines is quite high, right? So as a user, if you want to use IBM machine, you may have to wait for couple of hours until you get access, until your job is run on the IBM machine. And this is going to be a big problem for next couple of years, because people are really excited by quantum computing. They want to use quantum computers, but simply there are not enough quantum computers. One thing that can solve this problem is called multi-programming, and that's essentially as a user, you don't really use all the resources on a quantum computer when you are assigned the slot for running your computation. So why not support multiple users, right? That way we can improve the utilization, and that's something that classical computers already show that it's very effective. In data centers, one user is not just like there are multiple users using the same hardware, right? So can we do that with quantum computers? And I think it's possible, but at the same time, we should also think about uh, certain challenges, because people may be running sensitive compute on the quantum computer. There are IP issues. There are sort of sensitive data being generated on quantum computer. So one thing that we study a little bit is what are the vulnerabilities, like can someone steal data on a quantum computer? And this is something that we demonstrated with our recent work, where so what you see here as a graph is a Google's quantum computer. It has 54 qubits, and the way it's color coded is the nodes with the same color and number, they are attached to one wire. This wire goes to ADC, and then you do a readout, right? So basically, it's a multiplex system. And the reason multiplexing is really important is because you want to reduce number of wires coming from quantum computer to the classical FPGA, right? Because for some of the technologies, such as like Google's technology, these qubits are kept at very cold temperatures, and we cannot run large number of wires from qubits to the FPGA, right? So multiplexing is really important. But what this multiplexing creates is a side channel. So for example, let's say in this multi-programming setting, we have two users using qubits with this on this multiplex channel. Here, what can happen is one of the user becomes, adversarial, and they try to read or they try to figure out what the other user is doing, right? And this is something that we call side channel. And we show that on a small 5 qubit quantum computer that MIT built, that on this machine, it's possible to steal information. We have not really demonstrated this on IBM machine or Google machine, but if you give enough access, I think adversaries can start sort of thinking about ways to steal information. So in this figure, what we show is you have these two attacker qubits denoted by A. They are controlled by the adversarial user, and qubits 1, 2, 3 are the victim user or the user which is producing some sensitive data, and attacker is trying to figure out what that data is. Without really accessing qubit 1, 2, and 3, the attacker can infer what is the data on 1, 2, 3. And we show that for different configurations, the efficacy of this attack changes, right? This is only for one machine, but I think moving forward, this can become a really challenging issue. So I think quantum computing is a truly full stack problem. We have to think about not just algorithms and devices, but we also need to think about operating systems, compilers, architecture, and that is something that we do as a group. Uh, we have been focusing on quantum compilers and runtime, control architecture, fault tolerance, and we typically go and publish our results at systems and architecture and these days security conferences. So at Wisconsin, we have several faculty members in CS department focusing on quantum information sciences. I work on architecture. We have Ausal Burgoti who works on compilers. Rishabh Goel works on cryptography. Dieter works on complexity theory, and Charles Yuan, who's going to join us in the fall, is thinking about programming languages and how we can enable programmers to do more with the existing quantum computers and future quantum computers. We also have Wisconsin Quantum Institute, which is spread across multiple departments. And in the physics department, we have Masters in Quantum Computing degree, where students learn how to build qubits, how to program quantum computers, and how to develop next generation quantum algorithms. Uh, with this, I'll conclude my talk, and if you have any questions, I would be happy to take those.
Thank you, Swamit. And we have a few questions in the posted. So let me kind of say the in the order. So the first question is that, but the FPGAs are purely classical, not quantum, right? So it is a hybrid quantum classical problem. No?
Yes,
Question mark.
that's right. So inherently, when you are thinking about building a quantum computer, you need uh, a control computer that controls these qubits. So it is all quantum computers are hybrid classical quantum computers in some sense. There is no pure, at least maybe in theory, it's possible to build a purely quantum machine, but all practical quantum computers require classical infrastructure.
Another question is, does the compiler run Python or other classical computing languages?
Yes, so compiler starts with the Python or high-level language primitives, right? But what this compiler does is it takes a high-level description of a quantum circuit and converts it into a pulse schedule, which you run on FPGA. So again, the compiler runs on a purely classical machine. It can run on my laptop. It just converts, quantum circuit described in one form to the other form that we can run using FPGAs.
The last question is the multi-programming different from the cloud service?
So in the quantum setting, yes, right now I don't think vendors are using multi-programming, but it is very similar to what people typically do with cloud computing. So in some sense there are similarities, but what's the key difference? The key difference is on classical machines or conventional machines, uh, we don't see any noise. It's very easy to not very easy, but it's easy to kind of determine if there is some interference. With quantum, devices are noisy, so it's really hard to figure out if someone is really attacking your system, if someone is trying to steal information. And this is so new that we have not fully figured out what are the side channels, what are the means of stealing information on quantum computer.
Okay, great. Thank you so much, Swamich, and thank you for the great talk.